It is incumbent upon every visionary and every practitioner of technology to ensure that future generations have a home. Humans are not the problem. Hubris is, greed is, complacency is. Now is the time to leverage what we know for the benefit of posterity.
Welcome to the Friends of Space Resources podcast, a place to explore space resource exploration and utilization. What is it? Why it matters? And why it's so vital to the future of space investigation. Each week here, we'll meet with a technical expert in the field of space resources to better understand and gain deeper insight into their field of study. Welcome your host, Valerie Eastman.
Hello and welcome to this episode of Friends of Space Resources. I'm your host, Caleb Eastman, standing in for Valerie Eastman today. Each week on our program, we host an expert in either space resources or related fields. Sometimes our guests are not directly working in space resources, but specialize in a relevant field here on Earth. In order for space resources to become a reality, we have to engage experts from a wide variety of disciplines. And to that end, I'm pleased to welcome Lou Amadio today onto the show. He is the development lead architect with Microsoft Robotics Group. I might have butchered that, Lou, but what I'd like to do is just give you an opportunity first to sort of give a little bit about your background and just kind of tell us a little bit about yourself.
Well, thank you very much for having me on the show. As you said, I'm the development lead and architect in the Azure Edge Robotics team. Robotics is a fascinating field and something that I've been personally passionate about since I was really young. In fact, I recently purchased a Hero 1 robot, which was the first robot I ever saw in early 80s, where I said, robots are real? These are things that actually are not just science fiction. It's been amazing how far we've come from that time, but also how good those robots were from the past. So I'm pretty excited to be here.
Thank you, Lou. You know, the interesting thing, you know, probably the most agreed upon idea in space resources is that it's pretty much all going to be automated. Just curious, you know, what are your thoughts in terms of sort of where the field of robotics kind of needs to go from here to be able to either both be more accessible to other people here on Earth, but also to help us be a spacefaring species?
Oh, that's a fantastic question. One of the things that I've actually struggled with in robotics is that there's robots today, which really aren't that much different than robots from 10, 15, 20, even 30 years ago. And the science fiction of robotics that everyone just assumes is right around the corner, that AI is just going to lead to these androids that are in the home or delivering to people in the environment. Where are we in that path from kind of I'll call it dumb robotics to these super intelligent, able to figure out things robots? And how do we go from those older style manifestations to where the science fiction is that we want to get to? So there is a bit of a crawl, walk, run that we have to go through. And I believe at some point, there's going to be an inflection point where we're going to see that hockey stick of adoption. And along with that hockey stick of adoption, we're going to see the radical changes to how robots are produced and a proliferation of use cases. This happened a lot in IoT. So there's actually a close analog to the Internet of Things. And what I personally believe was the catalyst for that was what I call the maker moment. This was a point in time when embedded systems and connectivity became easy enough and approachable enough that people took it on as a hobby. And then as it became a hobby, people built careers on top of it, built companies on top of it. And that idea of making things easy and connected led to this explosion of interest and devices that permeate our society today. I believe that there's an analog in robotics, and that's what I'm here to help foster, which is how do we get that maker moment of robotics? Now, I'll take it one step further and actually say, I actually believe that ROS is like the Arduino of robotics. And ROS 2 is actually going to lead to that catalyst. But we need to make it easier to consume. We need to make it easier to deploy and debug, and help improve the quality, and get it into people's hands and say, here's how you build the basics. And then here's how you build it a little bit more and a little bit more. And then once that cycle starts to get kickstarted, we'll actually see that that hockey stick of adoption and scenario building. So that's my pitch, and that's really what I'm excited about to do and bring to the community.
That's really interesting. I've never thought about ROS being the Arduino of robotics. Gosh, that just blew my mind. Sorry, I just, when you live with ROS, you really don't. I don't know that I've ever drawn a comparison from ROS to anything before. Drawing it to Arduinos is really fascinating, and I think that I'm probably going to lay awake and think about that tonight. So I guess that begs the question: is the I'll call it the Raspberry Pi of robotics in existence yet? Go ahead.
Yeah, that's a very good question. What is the hardware? If you look at the Arduino ecosystem in 3D printing, there's the wiring. The programming model for Arduino was a wiring, and that made it really easy to turn light bulbs on and get that I did something. Mm-hmm. But you also had hardware that interfaced with that really simple programming model to make it go, oh, well, I can make this move. And when I turn a light on, it's not just a pixels on a screen, it's a physical device that actually did that. There are lots of different companies working in this space on that very first step. And I actually think that between the Raspberry Pi 4 and the Jetson Nano and some of the stuff from AMD, we actually have the pieces in place that will take that people can actually buy today. With that 2 gig Jetson Nano, like you can, it's in the, I've got a little bit of money, I can buy this and actually start doing something really intelligent with it. And the Raspberry Pi has always been that $35 price point. And you can do some really powerful things with just with a Raspberry Pi and a Jetson Nano. Some of my favorite companies are producing extensions to that work with both of those units to actually add easy motor support and easy sensing support so that you can start to actually get information about the environment. But how do you get information about the environment, process it, do something interesting with it, and then make it do something? And that's the control loop that ROS enables. But you've used ROS, so it's not, you sit a 14 or 15-year-old in front of ROS, and it's kind of hard. So how do we get past that? ROS is hard to, let's make ROS easy, and then we can actually build on top of it and have that progression from, we hid a lot of the complexity to now you can start to open up the box and look inside of it and go, oh, well, I can take this piece out and replace it with this and make it actually even more expressive and more intelligent. And then you can train your own models and put them in the box, and suddenly your robots become much more interesting. So I think that's, we've been focusing a lot on the industrial and commercial personally, mostly because that's where the money is. Mm-hmm. But even in commercial and industrial, there is a desire for simplified programming models and simplified end-to-ends that people don't want to think of it as a robotics. The robots are a means to an end. What's the end? And that's that's the conversation I think we're having today, is what are the various ends that we can target when we have that migration from I can create something, I can make it smarter, I can make it do more things. Where does it go? And I think that's really an exciting time. And this is where I think robotics is different today than it was even 10 years ago. And it's a great time to be working in this space. But like all hardware, it takes a long time to actually bring hardware and software and ecosystem to a place and make it that interesting part. So how do we actually keep the fire on until that hockey stick happens and people go, of course we should have been doing this.
So, so speaking of which, this brings up, I'll say two questions. I'll save this safety question for a little bit, because I'll be interested in things like the commoditization of force torque sensors and things like that. But my first question, the first sort of thing that I'm just, I've always wondered, and maybe you've been dealt with a lot of like you mentioned, the commercial enterprise space. I noticed that in consumer robotics, they tend to do very well in human robot interactions. Cosmo comes to mind in particular as it relates to how well they did. But when you get into enterprise robots, or robots with any kind of payload or any kind of capability, they toss the human robot interaction side away, which I don't really understand, because humans in enterprise is not going away. So I'm curious, why is it, do you think, that human robot interactions in the enterprise space sort of just like it seems like no one thinks about it?
So you bring up a fantastic point, which is well, for one, human robotic interaction is really hard. And when you bring a home robot or a robot into the home, it's all about that human interaction and that human connection. When you bring it into commercial, it's more about what the problem they're trying to solve. And solving those problems tend to be a lot hard by themselves. So you take these two hard problems and you try and put them together, you end up with an even harder problem. So home robots tend to focus on the human interaction. Commercial and industrial tend to focus on what they're trying to do. And most importantly, in those cases, you touched on safety. They need to be able to achieve their goal safely and efficiently 100% of the time. And anything less than 100% of the time is failure. And in some cases, that failure can be catastrophic. So when you have limited resources and you're trying to focus on achieving a mission, achieving a goal 100% of the time without failure, so things like making it easy to use tend to take a back seat. So how do we fix that? Well, the first part is, how do we actually make it easy, kind of like an add-on, like, here, just drop this in and you get robot interaction. Don't even have to think about it. So how do we actually make that a reality? How do you make it visceral? We have some work streams around virtual and mixed reality in robotics. How do you make it visceral so that people who want to reach out and touch something can actually do it and get that feedback? So making it so that those are really just easy and even part of the infrastructure that you can just drop in and make happen, I think is the very first part of that. The second part you kind of touched on is, well, the other really hard problem is, how do you make these things safe? And that's a non-trivial, and unfortunately, a lot of people wait until the end of the project to try and graft on safety. So how do we actually make safety part of the development ecosystem, part of the developer process, just like we do with security? Security can't be add-on. You have to think of it from the beginning of the project. Same thing with safety. How do you make safety part of the infrastructure that you're building on top of? How do you make reliability part of the infrastructure that you're building on top of? make it easy to do continuous integration, continuous deployment, continuous simulation. Okay, we're actually validating every change all the time. So what's the next step? Well, how do we make it easy to interact with these things? Okay, well, how do we actually tell it what to do? How do we do this in a non-proprietary way? Okay, now we've got that, but somebody can give it a bad command and it might run into a wall or a person or destroy a product. So how do we actually make it so that those things are safe? And there is that triangle of, I guess it's more than a triangle, but those are all part of the equation, and they're all hard, and some of them require an ecosystem investment.
So now I'm going to sort of blend two answers you've given earlier into another question. I apologize for doing so, because
No, it's okay.
so we talked about the maker moment, and we talk about safety, and a lot of the fear that I've encountered in robotics has to do with, how can we make it safe for makers to be involved in robotics, or the maker community, because of the higher stakes. It was the other day, I'm friends with the CTO of ClearPath on LinkedIn, and you might have seen it where he said, "Hey guys, you can't just plug a LiDAR into a Nook, and you have to and make a robot drive. You have to have multiple sensors. You have to have filters. You have to have a safety circuit. This stuff's been around for 20 years. Don't just plug a LiDAR into a Nook and then, install it into, a robot that has a 200 kilogram capacity payload, and, he makes those robots. So I imagine that he's encountered this. So, I'm kind of curious, what your thoughts are on just that. I think the craziness of IoT, and how that maker mentality can be blended, or how we can provide that safety net, if you will, for makers, for the maker community, as if you will, to be involved in robotics at this level.
That's a fantastic. I am friends with I just blanked on his name, sorry. But we have been longtime friends with ClearPath Robotics. And they understand safety in warehousing and industrial spaces. They understand the problem. They've been here for a very long time. And they've encountered people who are like, why is it so expensive?
Right.
Why is this safety rated LiDAR $8,000? Why can't we just put a depth sensor on it for $200 and send it into the field?
Right.
Yeah, it's a hard problem. And there's a couple reasons for that. One, these sensors are complicated. They're very complicated, and they tend to be multimodal, meaning that there's actually multiple sensors that validate what you're seeing from the environment. They're also not built at scale. In fact, a lot of these sensors are hand built by really by skilled engineers who are handcrafting each one of these sensors. So how do we transition the sensing from something that is these one-off hand-built things to something that's scale? And that scale leads to less expensive devices. It's a chicken and egg problem. You can't just release an inexpensive device and expect there to be a lot of sales. So there is a growth that has to occur. But I also think that there's a size as well, and modes of operation. For example, you can build a small robot that if it ran at you in full speed and hit you, you would go, I've got a bug. But you put that same code on a 500-pound robot and it hits you and you're going to the hospital. So there is a size scale where you can build robots that operates relatively safely because they're just small. But when you transition up, that's when you start to think about, okay, well, how do I make sure that if any one sensor failed, that I have enough information on my other sensors to operate safely? How do I create the aggregate and fuse all of that sensor data and validate when something fails, what should I do about it? In a way that even if your operating system failed or your runtime failed or your composition failed, that it's still operated in a safe mode. And I think that safety and security actually go hand in hand here. Because I do think that counterfeit devices is actually a kind of a potential problem in the space where somebody ships a box that looks like a safety rated sensor and inside of it, it's not. How do you validate that that hardware itself is the hardware you think it is and can trust the data that comes off of it? On top of that, you have calibration issues. Well, what happens if one of those sensors actually is working, but it's pointed in the wrong direction? How do you verify the calibration of these sensors? So to take a step back, I still think that there's a maker moment for smaller robots. And I think that there's an infrastructure required to make safety rated components less expensive for use once that hockey stick happens. That hockey stick is really going to be dependent on ubiquitous, safety rated, inexpensive components. And I think that that is the chicken and the egg problem, where we have to demonstrate on one hand the market, but also build the infrastructure to support, or the ecosystem to release those devices.
So speaking of which, since we're on the topic of sensors a little bit, you know, I've thought a lot about sort of, we'll just use the moon as an example, with the extreme cold, high contrast, you know, motors spinning at really fast RPM. So, you know, 360-degree LiDAR is probably you know, so, you know, if you had to guess in terms of whether it's stereo cameras or solid state LiDAR or far field, you know, infrared, if you had to guess, what do you think is going to be, you know, the best bet for autonomy in, I'll call it, troubled environments, hazardous environments, right? Or extreme cold, extreme heat, you know, sort of how we have industrial rated computers and things like that. What do you think that and obviously there are, you know, industrial rated sensors, but what do you think is the technology, if you will, that would, you know, give us the best eyes and ears for robots that are heading into the kinds of environments that will encounter sort of like on the moon or Mars?
I'll even take that one step further and say that there are hostile environments on Earth that would benefit from those as well.
Right.
And I think the answer kind of is D, all of the above. That it is going to be these multimodal components where some sensors are really great at low contrast, but they don't work really well in high contrast. There are some sensors where reflection is really a problem, but others where the resolution is lower, but it actually works better with reflections. So I think that for hostile environments, you're going to need multimodal sensors. Are they in one box or are they distributed components? I'm more of a compositional kind of person, so I do think that it is going to be a composition of devices, but at that point, calibration becomes incredibly important. Right. Now, I'm going to double click on that one because I think a lot of people really underestimate the importance of calibration of all of these sensors and keeping them calibrated. So calibration needs to be a constant part of the equation,
right?
Whenever possible. So.
Drift's a problem. I started my career calibrating what they call AGA3 compliant natural gas measurement tube. So you had to actually bring a tank of air with you and calibrate the sensor because it would drift. It's really you're right. I think that it's not a topic that a lot of people appreciate. And so I think it's probably something that we should spend a little time on here is calibration and why and why that should not be forgotten. The calibration and like you mentioned with multimodal sensors, proper application of sensor fusion. Those two topics don't get a lot of play. Sensor fusion probably gets a little bit more play than calibration, but it's is what do you think? What do you think are probably some of the, I'll call it the underappreciated skills, if you will, for I'll call it robotics development, and yeah, I'll just stop there. For robotic development, what are the underappreciated skills? Yeah.
I like to say that a robot is taking the hardest mechanical problems, the hardest electrical problems, the hardest software problems, the hardest AI problems, the hardest computer vision problems, putting them together and then expecting them to all just work together. I think there's underappreciation in each one of those disciplines, as well as the integration and application between robots. So, these multi-robot behaviors. Comes back to people expecting science fiction or delivering, technology from the 80s. But the space between where we are today and where we need to be is filled with innovation at each one of those levels. So mechanical engineering or mechatronics is a big one. AI, we're still at the infancy in AI. And I think I've recently was saying that AI is kind of the modern equivalent of being able to code a binary tree. Kind of everybody does it now. Really? So saying that you're an AI person is kind of expected. But what does it mean, and how do we apply it? But also, how do we improve it and diagnose it and understand what's going on inside of it? Those are all hard problems that I don't think we really have good solutions for today. I also think that there's algorithms on top that are emerging that will will help us solve a lot of these hard robotics problems. Quantum algorithms turn out to be a thing, not just applied to quantum computers, but actually applied to robotics and sorting, and those things are mind-blowing. But those are built on top of all of these other features, and something that I think more people will start looking into, which is how do you apply these algorithms, the composition of different kinds of computer vision and AI together with these new algorithms.
So you're kind of bringing up a really interesting concept, and particularly in the integration perspective of robotics, is what seems to be a generally underappreciated skill is the ability to sort of, I'll call it, exploit architecture as well. So ROS being an example of knowing ROS all by itself. In one there's one that you brought up earlier around knowing that a safety sensor, how to know that the safety sensor was indeed the real thing versus versus a fake. And so the Intel and ARM both have the hardware root of trust, on-die, and TPM supply chain hash that you can get out of the TPM or the on-die chip. Those security architectures that let you know, okay, let the manufacturer say this is the real thing, and then do you feel like this skill of really deeply understanding the things that have been built before is becoming a lost art, and exploiting that properly is becoming a lost art? It feels to me like it is, and I don't know if it's just me or.
So early in my career, I worked on the Windows shell, and there was a story where I was responsible for making the case to support high resolution, high color alpha blended icons in the Windows shell. And I checked this code in, and Windows start performance tanked. It's like, what? why did it tank? Well, it turns out that you have to pre-multiply the bitmaps when they start up, so that you actually take, you only have half the equation when you blend the icons, even if it's hardware accelerated. So I wrote some MMX code back in the day, assembler, to actually do this pre-multiplication, and I actually sped up Windows in the process. But people were mad at me because they just spent the last 10 years removing as much assembler from Windows as possible, and here I'm adding new assembler. But there are still people who write assembly today, but there are lost art as you go up the stack, and I think that a lot of people don't look under the covers on how things work or why things work, and may not necessarily use infrastructure appropriately for what the problems they're trying to solve, or trying to apply technology that works great over here, like cloud technology. Let's take cloud technology and drop it on a robot, and or have our control systems up in the cloud. Yeah, latency. There's things in here that latency kills. It really does, and I don't say that lightly. But there are things that you have to run. You can't just take technology that wasn't intended for one scenario and run it in another scenario. And I do think that's part of that lost art of, well, how do I know this, but what's more appropriate over here?
So yeah, so this is the really interesting thing to me, is the, you mentioned, what we call, latency, or we'll call, temporal isolation, and safety isolation in the control layer, particularly when you're dealing with, real-time control systems.
We should touch on real time in a second.
Okay, well, yeah, I do want to, because the whole real-time thing, and particularly when we talk about, how software defined everything versus preemption in real time, is really interesting. I do want to talk about that. I am curious, while where do you think the balance is? As I was going to ask earlier, when we were talking about how hard ROS is, how much effort is being placed into abstracting ROS, but now I'm like, wait, this is part of the problem, is abstracting all this stuff means you don't understand it very well, or people up the value chain don't necessarily understand it very well. And so where do you think the balance is between abstracting this really hard stuff into more user-friendly, more accessible things, but being able to defend, if you will, the complexity that is inevitable, sort of the further down the stack you go? Where do you think that balance is as it relates to I'll call it the accessibility versus oh my God, did they just do that safety thing?
Honestly, I don't think that there's one good answer for that. I am a fan of what has been termed a leaky abstraction, which is,
okay,
I built something on that helps you out, but I know that I will not be able to replace everything under the covers. So when I build my abstractions on top, I have to give you a escape valve and being able to poke at it underneath. And I worry that, there's this this XKCD article that's like, oh, there's 12 standards. Well, we need one to replace them all. And now we've got 13 standards. If you built that standard that says, oh, well, I can access number 12, then your abstraction's small, but then you open up the thing under the covers. I'll give you a more concrete example. So we have a ROS node called the Onyx runtime, that we call the Microsoft's Onyx runtime ROS node. Onyx is a format for representing machine learning models that include the topology of the ML model plus your weights and measures and all, and support data. So you can take the Onyx model and use under the covers Windows machine learning or TensorFlow and the TensorFlow graph to take that Onyx model and hardware accelerate it, right? So you're already like 6 levels up by the time you use our ROS node.
Right.
And then we've set in our ROS node said, well, we're going to process the inputs, send it into the Onyx runtime, and then process the outputs. So at the end of the day, you give us a machine learning model and connect us to a camera, and we'll start outputting markers, so ROS markers. Yay, right?
Right.
That is an abstraction that I think makes it really easy to say, hey, I want to go track my cat because, YOLO V2 has cat.
Right.
So if I see cat, turn the robot towards the cat and go drive at it, right? So, but when you start going, okay, well, that's not really useful because I need to look at at the numbers of a valve to see where the pointer is. So I know whether or not I actually need to go reach out and grab the thing to turn it. It's an abstraction that's designed to be easy to use, but it doesn't replace the fact that you can run Onyx runtime. You can go do your own hardware accelerated ROS node. So we've built an abstraction that makes it easy, and we can package that together and say, here, you just drop it on a robot and suddenly you have a cat tracking robot.
I want to go have a look at that node because I didn't know that existed, but
yeah.
But
we're in the process of moving it to ROS1 and adding deep pose support. So
I will say I absolutely love the concept of leaky abstraction, and that I don't know that I've ever heard it articulated quite so well, but that has been something that I've always preferred an abstraction that let me sort of go, dig under the covers when necessary to see what it's doing. So yeah, I love that leaky abstraction. It's cool, but
yeah.
but
I can't take credit for that one. That was one of the coding philosophy books. I can't remember which one it was, but leaky abstractions. And I used to buy the book and hand it to new people, but can't find it anymore.
This isn't one by was it Uncle Bob? Is it the guy who made Agile?
No, I think it was the Frog Software.
Okay.
I forget the name of it. It's gonna drive me nuts. I gotta go find the book.
So we won't have much time left. I do want to go back to real time.
Yes.
Yes. So real time is effectively a necessity for anything, for some part of any robotic system, right? And that's not going away. And so, just let me know what I guess just give me your thoughts on sort of real time in a world of abstraction, in a world of we'll call it software defined everything. And
awesome.
And then yeah.
So I was at a maker fair talking about Windows and IoT, and somebody walked up to me and said, well, does it support real time? I said, well, what do you mean by real time? And they said, well, we need to know within 10 minutes of an event.
Whoa, that's
well, okay. And for that person, real time meant I had to know that it happened within 10 minutes of an event. Okay. So other people, I need to know when it happens within a minute of an event. When you're talking about safety, that baked into the safety standards, within 1 millisecond of something happening, you have to be able to stop or start stopping the robot. And so real time, unfortunately, doesn't have a lot of meaning when you look at it from what people expect of the phrase real time. So I've actually started using the phrase time domains because it implies not just what is your window, but how much jitter and how much latency is implied by the time domain. Okay, so for example, a camera time domain, well, really means that it has to happen about 30 frames per second and you have to be able to process it before the next frame comes. So your camera time domain defines your window of operation. the millisecond time domain. I have to be able to process something within 1 millisecond. Nanosecond time domain. Oh, I mean, that's where you start to really, like, that's where most people who say real time think of the time window. But you can also say, well, some of these events, I don't really need to know for days. Okay, so, but I need to know exactly what time it happened, and I need to know all of the events that led up to it. And I need all of those events to have real time associated with them. So I've referred to time domains, which actually gives us that window and jitter and latency requirements. So now what? Well, it turns out that a robot is actually made up of a hierarchical time domain or hierarchical control loops, each of which have their own temporal requirements. Okay, so if you're processing the signals coming off a motor in order to maintain torque, you need to process them in nanoseconds, or at least microseconds, right? So now you're processing down here, but if I'm driving and trying to localize myself, I'm not going to get much better than 30 frames per second, maybe 60 frames per second or 100 frames per second, but I need to be able to geo-lock myself visually while I'm telling the motors what to do. And those are different control loops, but each one has to operate in their own time domain.
It's interesting. I actually encountered this same problem, the same problem of talking about, the difference between, what marketing real time versus, and I typically, what the term that I use for is what I call the control frame. So the control frame is the period of time where work has to be done given the inputs and the latency requirements and the jitter requirements. That's all set within a control frame, and that control frame is respective of a particular control problem or a particular. So this, I like your time domain. So that's of course, and like you said, a robot consists of many time domains.
And when you're telling a robot what to go do, that operates in a different control loop altogether. So, hey, move that box from over there to over there. Tell me when you're done. It could take an hour before you know when it's done. So that's a different time domain altogether.
So the autonomic versus strategic part of it's really interesting. So I guess, I'll say last question, just sort of in your view, what do you think are the fields of study, either within robotics or generally, do you think is the most useful, I'll say, for getting us sort of accelerated, I'll say beyond Earth's atmosphere from your perspective?
I wish I had a good answer for that, because honestly, I would say all of them.
Right. Sure. I don't know why that was a really unfair question.
No, it's if somebody came to me and said, "Hey, I love robots. What should I study?" It's a really hard question, because honestly, there's innovation happening on all of those levels, and even out of those skill sets are useful outside of robotics as well. I mean, robotics is a control systems theory, industrial theory. These things are actually useful not just for the on-robot scenarios, but also between robot scenarios, and even just, hey, I need to program a conveyor belt to move material in my factory. It's kind of you have an AI camera on here that tells you how fast you're moving, or what if there's problems with the material. So honestly, I don't really have a good answer for that. You're not going to get wrong studying mechatronics, electronics, computer science, AI, computer vision, industrial control theory.
Thank you for listening to the Friends of Space Resources podcast, and welcome. Connect with us on social media by searching the Friends of Space Resources podcast, and join us online at friendsofisru.com. Check back weekly for new episodes and new insights into space resources. Until next time, look up and keep dreaming.